Welcome! In this session, we will tackle problem number 398, titled Random Pick Index. We'll dive into the problem statement, explore various approaches to solve it, and analyze the complexities involved. Let's get started. In this problem, you're given an integer array called nums, which is sorted in non-decreasing order. Your task is to implement a solution that can randomly pick one of the indices where a specified target value appears in the array. The important part is that if the target value occurs multiple times in the array, each of its indices must have an equal probability of being chosen. To achieve this, you'll need to implement two functions. First, a constructor that initializes the object with the input array nums. And second, a pick method that takes the target value as input and returns a random index where the target is located. Note that the problem guarantees the pick function will only be called if the target exists in the array. The pick function is expected to return an integer representing a randomly chosen index from nums where the value matches the specified target. Let's go through some examples to understand this better. In the first example, we have nums equals 1, 2, 3, 3, 3. If we call pick 3, the function should pick one of the indices 2, 3, 4, where the number 3 is found. Each index should have an equal chance of being selected. For instance, calling pick 3 multiple times might produce outputs like 3, 4, 2, 4, 3, where the indices are chosen randomly. In another example with nums equals 1, 1, 1, 2, 2, calling pick 1 will return one of 0, 1, 2, and calling pick 2 will return one of 3, 4. Again, the probability of selecting any particular index in these sets must be uniform. Continuing with another example, if nums equals 4, 4, 4, 4, and we call pick 4, the number 4 is present at all indices 0, 1, 2, 3. The function must return one of these indices uniformly at random. This means that every call to pick 4 should give equal weight to all these indices, ensuring a fair distribution. Now, let's discuss the constraints you need to keep in mind. The array nums can have a length of up to 20,000 elements, and the values in the array can range from -231 to 231. These constraints require your solution to be efficient, as it needs to handle large input sizes effectively while maintaining uniform randomness. There are also several edge cases to consider. For instance, if nums contains only one element, such as nums equals 5 and target equals 5, the function should always return the only available index, which is 0. If all elements in the array are the same, like nums equals 7, 7, 7, the function should still choose indices randomly and uniformly from 0, 1, 2. When the target appears only once in the array, such as nums equals 1, 2, 3, with target equals 2, the result must always be the single valid index deterministically. Lastly, for very large arrays, your solution must remain efficient in both time and space, ensuring that it handles up to 20,000 elements without compromising performance. The main takeaway is that your implementation should guarantee uniform randomness while adhering to these constraints and edge cases. To begin, let's consider the brute force approach for solving this problem. The idea is straightforward. We iterate over the entire array and collect all indices where the target value appears. These indices are stored in a separate list, and once we have this list, we can randomly select one of the indices using a built-in random number generator, such as random.choice in Python. While this method ensures that we can pick a random index correctly, it does come with some trade-offs in terms of efficiency. Specifically, the time complexity of this approach is O(n), as we need to traverse the entire array once to collect the indices. Additionally, the space complexity is O(k), where k is the number of occurrences of the target in the array, because we need extra memory to store these indices. This makes the brute force approach both simple and effective for smaller arrays, but it can become less practical as the size of the array or the number of target occurrences increases. Now, let's discuss the trade-offs and introduce a more efficient method called reservoir sampling. While the brute force approach is easy to implement and works well for small arrays, it becomes inefficient for larger datasets because of the additional space required to store indices. Reservoir sampling, on the other hand, addresses this limitation by allowing us to pick a random index on the fly, without the need to pre-compute and store all target indices. Here's how it works. As we traverse the array, we maintain a variable called count to track how many times we've encountered the target so far. For each occurrence of the target, we generate a random number within the range of 1 count. If this random number equals 1, we update our result to the current index. This ensures that each target index has an equal probability of being chosen. With this method, we achieve the same O and time complexity as brute force, but we reduce the space complexity to O1, as no additional memory is used for storing indices. There are some key observations that make the reservoir sampling approach particularly effective. First, it guarantees that each index of the target is selected with equal probability, which is critical for ensuring fairness in the random selection. By eliminating the need to store all indices, this approach is highly space efficient, making it ideal for scenarios where memory usage is a concern. The uniform probability is achieved because, at each step, the current target index is chosen with a probability of 1 divided by the count of targets encountered so far. This mathematical property ensures that every index has the same chance of being selected as the traversal progresses. While the implementation is slightly more complex than the brute force method, the memory efficiency and suitability for large arrays make it a worthwhile trade-off, especially when working with datasets that exceed memory constraints. Given these considerations, the reservoir sampling approach is the strategy of choice for this problem. It offers several key advantages. First, it is highly efficient in terms of space, requiring only O1 additional memory, which makes it particularly well suited for handling large arrays. Second, it guarantees uniform probability, ensuring that each occurrence of the target is equally likely to be selected, which is essential for correctness. Third, it is scalable, as it avoids the need to store indices in memory, making it practical for environments with limited resources. While the brute force approach is simpler to implement and can work for smaller datasets, its reliance on additional memory makes it less favorable for larger inputs. Reservoir sampling provides an optimal balance between time efficiency, space optimization, and scalability, making it the most effective solution for this problem. In this problem, we're given an array of integers, nums, and a target value, target. Our goal is to randomly select one of the indices in the array where the target appears, ensuring that each index has an equal probability of being chosen. The brute force approach to solve this involves two main steps. First, we iterate through the array to find all the indices where the target appears. For every element in nums that matches the target, we add its index to a list, indices. This step has a time complexity of O(n), where n is the size of the array. Once we have the list of indices, the second step is to randomly select one of these indices. Using a random number generator, we can pick an index from the indices list uniformly. For example, if the list contains 2, 4, 7, we generate a random number between 0 and the length of the list minus 1, then use this random number to select an index. The random selection is a constant time operation, making this step O(1). Finally, we return the randomly chosen index as the result. While the brute force approach works, it requires additional space to store the indices list, which might not be ideal in scenarios with memory constraints. To address this, we can use an optimized solution called reservoir sampling. This approach eliminates the need to store all indices by allowing us to select an index in a single pass through the array, with equal probability for each occurrence of the target. Here's how it works. We start by initializing two variables, result, which will store the selected index, and count, which tracks how many times the target has been encountered. As we loop through the array, whenever we find an element that matches the target, we increment the count. For each occurrence, we decide whether to select this index based on a random number. Specifically, we generate a random number r between 1 and count, and if r equals count, we update result to the current index. This probabilistic replacement ensures that each index has an equal chance of being selected. After completing the loop, the result variable contains our randomly selected index of the target. Reservoir sampling ensures that each index of the target is chosen with equal probability. The way this works is rooted in the probabilities assigned during the traversal. When the first occurrence of the target is encountered, it has a 100% chance of being selected because it's the only candidate. When the second occurrence is found, it has a 50% chance of replacing the first, as the random number generation ensures fairness. For the third occurrence, it has a 1/3 chance of replacing one of the first two, and this pattern continues for subsequent occurrences. This approach guarantees uniform randomness without needing to store all indices. Additionally, the space optimization is significant. Unlike the brute force method, which requires k space to store the indices, where k is the number of times the target appears, reservoir sampling uses only 1 space. This is because it relies solely on primitive variables like result and count, making it highly efficient in terms of memory usage. No additional data structures are needed, which further simplifies the implementation. Let's break down the complexity of both approaches. For the brute force solution, the time complexity is n to traverse the array and collect the indices, plus 1 for the random selection, resulting in an overall complexity of n. The space complexity, however, is k, as we need to store the list of indices where the target occurs. With the optimized reservoir sampling approach, the time complexity remains n, since we still perform a single pass through the array, but the space complexity is reduced to 1, because no extra space is required. Now, we also need to consider edge cases. First, if the target does not appear in the array, the algorithm should handle this gracefully, perhaps by returning -1 or throwing an exception. Second, if the array contains only one element and it matches the target, the algorithm should always return that index. Finally, if all elements in the array are equal to the target, the algorithm must still ensure uniform random selection across all indices, maintaining fairness in the output. Let's walk through an example to solidify our understanding. Suppose nums equals 1, 2, 3, 3, 3, and target equals 3. We start by initializing result to -1 and count to 0. As we iterate through the array, we skip the first two elements since nums 0 and nums 1 are not equal to the target. At I equals 2, we find that nums 2 equals the target, so we increment count to 1. Since this is the first occurrence, we randomly select it, setting result to 2. Next, at I equals 3, we encounter another target, so we increment count to 2. Now, there's a 50% chance of replacing the current result. Finally, at I equals 4, we find yet another target, incrementing count to 3. Here, we decide whether to replace result with a 33.3% probability. After completing the iteration, the result variable holds a randomly selected index, such as 2, 3, or 4, ensuring uniform randomness as required. This implementation solves the problem of randomly picking an index for a given target in the array nums with equal probability. The solution is implemented as a class-based design. Here's the step-by-step explanation. 1. Initialization, __init___ method. The constructor takes two inputs, the array nums and the target. It stores these inputs in self.nums and self.target for later use. It also pre-computes a list of indices where the target appears in the array. This is achieved using a list comprehension that iterates through nums with enumerate, appending the index I for every element that matches the target. The pre-computation ensures efficient random selection later. 2. Random pick method. This method is designed to select one index from the pre-computed list self.indices uniformly at random. It uses Python's random.choice function, which selects an element from the list with equal probability. The choice is both simple and efficient, leveraging Python's inbuilt randomness capabilities. ### complexity analysis. Pre-computation, __init___ method. The list comprehension iterates through the entire array nums, making this step n, where n is the length of nums. Index selection, pick method. The random.choice function operates in 1 time because it accesses a single random element from self.indices. ### edge case is handled. If the target does not exist in nums, the self.indices list will be empty. In practical scenarios, it is assumed that the problem guarantees the presence of the target in the array. However, if the guarantee is removed, additional validation, e.g., raising an exception when self.indices is empty, can be added during the pick method. This solution is both efficient and elegant, leveraging pre-computation to ensure that random selection is performed in constant time. This is the Java implementation for LeetCode problem number 398, Random Pick Index. The logic mirrors the Python implementation. The constructor initializes the input array, target value, and pre-computes the indices of the target in the array using an array list.
The pick method uses Java's random class to select a random index from the pre-computed indices.
Notable differences from Python include explicit type declarations, the use of ArrayList for dynamic storage, and the random class for random number generation.
To solve this problem, we start by initializing the solution class with the given nums array and target. Here, nums is 1, 2, 3, 3, 3, and the target is 3.
During this initialization step, we pre-compute all the indices where the target appears in the nums array. This is achieved using a list comprehension that iterates through nums and collects the indices of all elements equal to the target.
In this case, the indices of 3 are 2, 3, 4. Now, when we call the pick method, it randomly selects one of these indices from the indices list. For example, if the random selection picks the value at index 1 in indices, the result corresponds to nums 3, which is also 3. Therefore, the final output of this call would be 3. In the next example, we initialize the solution class with nums set to 5, 5, 5, 1, 1, 5, and the target is 5. Again, during initialization, we pre-compute the indices where the target appears in the nums array.
Using the same list comprehension as before, we find that the indices for 5 are 0, 1, 2, 5. When the pick method is called, it randomly selects one of these indices. For instance, if the random selection returns the value at index 0 in the indices list, the result corresponds to nums 0, which is 5. Hence, the final output in this case would be 0. This process ensures that each occurrence of the target has an equal chance of being selected. In the third example, we initialize the solution class with nums set to 10, 20, 30, 40, 50, 10, 10, and the target is 10. As part of the initialization, we determine all the indices where the target appears in the array. Using our list comprehension, we find that the indices for 10 are 0, 5, 6. Now, when we invoke the pick method, it selects an index randomly from this list.
For example, if the random selection picks the value at index 2 in the indices list, the result corresponds to nums 6, which is also 10. Consequently, the final output in this scenario would be 6. This demonstrates how the solution works consistently across different examples, ensuring randomness and correctness. In this solution, the time complexity is determined by two main operations: the pre-processing step and the constructor and the pick method. Let's start with the constructor, where we take the input array nums and the target value. The constructor iterates through the entire nums array to identify all indices where the value matches the target. Since this involves a single traversal of the array, it takes n time, where n is the length of the array. Additionally, storing these indices in a separate list requires k time, where k is the number of occurrences of the target in the array. However, because the traversal dominates, the overall time complexity of the constructor is n. Now, for the pick method, it utilizes the pre-computed indices list and selects a random element from it using the random.choice function. Since this operation is constant time, the pick method has a time complexity of 1. Combining both, the overall time complexity is n for preprocessing, and if the pick method is called m times, the total time complexity becomes n plus m. The space complexity of this solution is primarily influenced by the memory used for storing the nums array and the indices list. First, the nums array is retained as an instance variable, which requires n space, where n is the length of the array. Next, we store the indices of all occurrences of the target in a separate list. In the worst-case scenario, where every element in nums matches the target, the size of the indices list will also be equal to n, requiring k space, where k is the number of occurrences of the target and can be as large as n. Thus, the total space complexity is n, as the storage of both the nums array and the indices list dominates the memory usage. To better understand the efficiency of this solution, let's compare it with a naive approach. In the naive approach, every call to the pick method would involve iterating through the nums array to dynamically find all indices of the target. This would take n time for each call to pick. If pick is called m times, the total time complexity would be n asterisk m. Additionally, the naive approach has a space complexity of 1, since no extra storage is required. In contrast, the optimized approach preprocesses the indices of the target in n time during initialization,
and each call to pick operates in O(1) time due to the pre-computed indices list. This reduces the overall time complexity to O(n plus m) for m calls to pick. While the optimized approach does incur an additional space complexity of O(n) due to the indices list, the improvement in time efficiency makes it much more practical for repeated calls. To mathematically validate the big O analysis, let's consider the operations involved. During preprocessing, the algorithm performs a single traversal of the input array nums, which is a linear operation, resulting in O(n). The pick method, on the other hand, is a constant time operation that runs in O(1), regardless of the size of the array. When the pick method is called m times, the total time complexity is the sum of preprocessing and the m constant time calls, O(n) plus O(1) asterisk m, which simplifies to O(n) plus m. As for space complexity, it is dominated by the storage requirements of the nums array and the indices list, both of which require O(n) in the worst case. Breaking this down by scenarios, in the best case, the target has very few occurrences, leading to a smaller indices list and reduced memory usage, though the overall time complexity remains O(n) plus m. On average, the target occurs in a fraction of the array, maintaining O(n) preprocessing time in O(1) for each pick call. In the worst case, where every element in nums matches the target, the indices list grows to size n, but the time complexity remains O(n) plus m, while the memory usage peaks at O(n). In summary, the optimized approach offers significant improvements in efficiency for repeated calls to the pick method compared to the naive solution. While it does require additional space to store the pre-computed indices list, this trade-off is justified by the substantial time savings, especially for large inputs and multiple method calls. By pre-processing the indices in O(n) time and enabling O(1) random access during each pick call, the solution effectively balances pre-processing costs with runtime efficiency, making it highly suitable for scenarios involving repeated random selections. When tackling this problem, there are several common mistakes to watch out for. First, incorrect random selection logic is a frequent error. For example, you might think using random.choice on a pre-processed list of indices will work, but if the pre-processing step is flawed, it could introduce biases, leading to uneven randomness. It's essential to verify that your randomness distribution is truly uniform. Next, skipping edge cases is another pitfall. For instance, what happens if the input array is empty or the target value isn't present? These scenarios can easily cause runtime errors, so always check the constraints and explicitly handle these cases in your code. Another issue is ignoring space constraints. A brute force approach that stores all indices of the target in a list can quickly become memory intensive for large datasets. Instead, strive for space-efficient solutions. Similarly, failing to optimize for time is a concern. If you repeatedly iterate over the array to find indices, you're wasting computation time. Whenever possible, aim for a one-pass solution. Finally, overcomplicating your logic can hurt both readability and performance. Avoid unnecessary data structures or helper functions, and focus on keeping your solution clear and concise. Now, when preparing for interviews, there are key insights to keep in mind. First, recognize that problems involving random selection often require a balance between space, time, and randomness constraints. Mastering techniques like reservoir sampling will give you a significant advantage. It's also important to be ready to discuss trade-offs. For example, when should you preprocess the array to store indices, which uses O(n) space, versus dynamically selecting indices on the fly, which uses O(1) space? These decisions can vary based on the problem constraints. Additionally, communication is critical. Explain how your solution ensures uniform randomness and how you've accounted for edge cases. This demonstrates both the correctness of your approach and your thorough thought process. Don't hesitate to ask clarifying questions either. For example, ask whether the array is sorted, contains duplicates, or has a maximum size limit. This can help you tailor your approach effectively. Finally, explore related problems to strengthen your understanding of random selection techniques. For instance, solving problems like random pick index, linked list random node, or random pick with weight will deepen your familiarity with these concepts. Alternative approaches to this problem often involve trade-offs between preprocessing and runtime efficiency. One common method is preprocessing with index storage. Here, you store all indices of the target value in a list during a pre-processing step. Once this is done, selecting a random index becomes a simple O(1) operation. However, the trade-off lies in the space complexity, which is O(k), where k is the number of target occurrences. While this can be space efficient for small arrays, it may become memory intensive for larger inputs. Another approach is reservoir sampling, which is particularly useful when memory is a concern. In this method, you traverse the array once, maintaining a single candidate index that you update probabilistically as you encounter new occurrences of the target. This approach is highly space efficient, using only O(1) space, with a time complexity of O(n). However, it requires a solid understanding of how to maintain uniform randomness during the traversal. Each of these methods has its strengths, and the choice often depends on the specific constraints of the problem. A third alternative approach leverages binary search on sorted arrays. If the input array is sorted, you can use binary search to quickly find the range of indices where the target value occurs. Once the range is identified, you can randomly select an index within this range. This method is efficient, with a time complexity of O log n for the binary search and O(k) for the random selection of an index. Additionally, it has a space complexity of O(1), making it memory efficient. However, the applicability of this approach is limited to sorted arrays. If the input array is not sorted, you would need to pre-process it, which could add overhead. This approach is a great option when the array is already sorted or when sorting the array upfront aligns with the problem requirements. Each technique, whether pre-processing with index storage, reservoir sampling, or binary search, has its own trade-offs, so understanding the problem constraints is key to choosing the most effective solution. Great job! We've successfully reviewed problem number 398, explored the brute force approach, and discussed its trade-offs. Remember, mastering these foundational methods is key to building more efficient solutions in the future. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!